You're gonna have to give focus here because I know there's a little bit of text here, but it's important to understand this. So it's a real-time data acquisition system, which basically is receiving a input about the mechanical position that is limited to a maximum movement frequency of 10 Hertz. Okay, all right. Every 10 Hertz, we are getting a input about some mechanical position of something. The input signal varies between -5, so it could be anywhere between -5 to 5 volts. The sample rate is 100 samples per second. So this data acquisition system is receiving data of 100 samples every second. All right, we have to design a slew rate check on input data that will detect any sample that differs from its predecessor by more than would be possible for a 5-volt peak. So the peak voltage of 5 volt, 10 Hertz sinusoidal wave signal. Maximum rate of change for a sine wave occurs as the signal crosses 0 axis. Okay, all right. Find the Vmax, find the maximum voltage for a single sample as compared to its predecessor. That can be permitted by the rate check software. Okay, so the very first thing is to understand what exactly the slew rate is. And it's important to devices like op-amps. Okay, so when there's a change in the input, there's a change in the output. Now, how quickly your device reacts to a step change in the input voltage, the rate of change in the output voltage caused by a step change in the input voltage change as a function of input voltage changing, and this could be voltage or current, both, either. As the current or voltage at the output changes, at what rate, that is associated with the slew rate, and it's usually represented in volts per microsecond. So there's a very simple formula to calculate the slew rate. Remember, this is a sine wave signal. So Vin will equals here peak voltage times cosine. Actually, this is going to be sine here 2 pi ft. This is important here. 2 pi ft. Now let's plug in the values here because a lot of information here is known. Peak voltage is 5 here, correct? So let's put 5 here. Sine 2 pi, 2 times 3.14 times frequency, which is 1 Hertz. So if you do the math, it basically will come down to 62.8. Let's keep T as it is. Now, because slew rate associated with the change in the output voltage as a function of change in the input voltage, we're gonna take a derivative here. So this becomes with respect to the time, Vn. So this will basically would become 5 will come over here. If you differentiate sine, it will come down as cosine of 62.8 t times 62.8, because remember we are doing it as a function of t. 62.8, and if I do the math, 5 times 62.8, it's actually going to give me 314 cosine of 62.8 t, correct? Right? Now, this is the magnitude that we were looking for. So, in other words, I can rewrite this as d over dt Vn, this is the max, remember, equals to 314. Now, since the sample rate was set to 100 samples per second, and we are only interested in, where was it? For a single sample for a single sample. So if I multiply that by 0.01, since we're doing 100 samples, so if I multiply this by 0.01, I basically would get 3.14. That is the maximum voltage for a single sample as compared to its predecessor that can be permitted by the rate check software. So there's a little bit of math that you have to do. Remember, this equation is pretty important. Plug in the values, take a differentiate with respect to time, and then multiply it by 0.01 here because they were interested in for a single sample. If they were not asking for a single sample, we didn't really have to do this part right here.